All right, log properties, part 1. Log properties. These are like your exponent laws, but they're for logs. A couple of them we've already seen. The first one that we've already seen are logs are exponents. So we have a equals b to the power of c is equivalent to writing c is equal to log base b of a. So when we're doing something like this, if you remember, if let's say 32 is equal to 2 to the 5th, to convert it to log form, you ask yourself, okay, what's the base? So you write log base, oh, the base is 2. What are logs? Oh, logs equal exponents. The exponent is 5, and then you've got your leftover number sitting in here. So those are equivalent forms. If you had something like this, y is equal to log base 6 of m, something like that. If you want to change it to exponential form, you ask yourself, okay, what's the base? The base is 6. What's the exponent? Well, logs are exponents, so the exponent has to be y, and our leftover number is m. So we can switch back and forth between logs and exponents. The second thing that we already know is this. If we have log base triangle of square, we know that this is the base, and so the triangle itself has to be greater than 0, and the triangle can't equal 1. We decided on the base for that. For the square or the argument, if you think back to the graph of y equals log of x or log base 3 of x or anything like that, that graph would automatically have a vertical asymptote line here at x equals to 0 and look something like this. So its domain would be x is greater than 0. It follows then that if you had log base anything of x, that the domain for that would be x is greater than 0. And so therefore, if you had log base anything of, let's say, a square, the square would have to be greater than 0. So what we get from that then is that when you have log base triangle of square of these sorts of things, the triangle is the base. The triangle must be positive. The triangle can't be 1. And for this guy, the square or the argument must also be positive. All right, third property. If we want to do our third property, we want to find, oh, hang on a second. I'll do that later when I do some examples. If we want to take a look at our third property is going to be evaluating logs. And so evaluating logs works like this. The easiest way for me to show you how to evaluate logs is for you guys to find the log button on your calculator. So if you do have your calculators in front of you or beside you somewhere, just grab them for a second. Maybe pause me and while you grab them. And I'm going to get you to find the log of some things. So we're going to find log of 10, and we're going to find log of 100, and we're going to find log of, let's say, 1,000,000. And we're going to find log of 0.1, and we're going to find log of 1 over 1,000. Okay, so what we do is we find that log button on your calculator. And if you have a regular calculator, you know, like a forwards calculator, just go log 10 equals, and we should get 1. If you go log 100, log of 100 equals, and we should get 2. And we get log of 1,000,000, log of 1,000,000, 1,000,000,000, 6. Log of 0.1, log of 0.1 will be -1. And log of 1 over 1,000, use the brackets, is going to be -3. So I'm going to tell you a secret. I did not use my calculator for those because I know that logs are exponents. And all of these things, the thing that all of these have in common, the 10, the 100, the 1,000,000, the 0.1, which is really 1/10, the 1 over 1,000, is that these are all powers of 10. So really what I'm doing here is I'm evaluating log of 10 to the 1. And I'm evaluating log of 100 is 10 squared. And I'm evaluating 1,000,000 as 10 to the power of 6. And 1/10 is 10 to the power of -1. And 1 over 1,000 is 10 to the power of -3. And because logs are exponents, out pops the exponent, the exponent, the exponent, the exponent, and the exponent. So this works with your log button. Now, that log button and the powers of 10 are related to each other. So the log button on your calculator is a base 10 logarithm. It is called the common log, or the common logarithm, even though it's not that common. I mean, it's more common than other bases, like 5, for example, but it is not the most common logarithm. But what we've just learned is that if I had log base 10 of 10 to the 6, out pops the 6. If I had log base 10 of 10 to the negative 3, out pops the negative 3. So therefore, we can change this up so it doesn't have to be base 10. What if I had log base a of a to the 6? As long as these bases are matching, just like these guys up here are matching, right? Out pops the 6. And as long as a of a to the negative 3, as long as the bases are matching, logs are exponents. And so what we get is that we get log base a of a to the x. Logs are exponents. Okay, let me show you how that works. We might see something like this, evaluate. So if we want to evaluate something, we're going to be taking a look at, let's try this one, log base 3 of 9. So the base is 3, so you got to make sure that you can get that base sitting in there. 9 can be written as 3 squared. So as soon as you can write that as a common base, logs are exponents, and so therefore the answer will be 2, because the 2 pops out since logs are exponents. If you wanted to have log base 5 of 1 over 125, you've got a base of 5. So you'd have to write this as a power of 5. This is 1 over 5 cubed, also known as 5 to the power of negative 3. Once you've done that, logs are exponents, and so out pops the exponent. Even if you had some more difficult ones, let's say log base 2 of the square root of 8. Ooh, that looks good. So again, the base is going to be 2, so I'd have to have log base 2 of, well, the square root of 8 is 8 to the power of, the roots are on the bottom, right? So 8 to the power of 1/2, that's not going to help me. So what I really want to do is I don't want to do that. I want to figure out what 2 to the power of. So 8 is 2 cubed, and I've got the square root of 2 cubed, which is 2 to the power of 3 over 2. Logs are exponents, and out pops my answer of 3 over 2. Now, there is a problem with this one. What if I have something that's more difficult, log base 4 of 8? Well, there's a couple of different ways that you could do this. You could realize that what we want is this, log base 4 of 4 to the something. So 4 to the something has to equal 8, and that's where we use those exponent equations that we did before. We get a common base. 2 to the 2 times something is equal to 2 cubed. So 2 times something is equal to 3. Divide by 2, that is equal to 3 over 2. So therefore we get log base 4 of 8 is really log base 4 of 4 to the 3 over 2. And out pops your exponent once your bases are the same. This does, though, seem like a lot of extra work, and you will find that logs have a ton of different ways of doing things and different properties that you can find and all that kind of stuff. So we could also use common bases. And so if we use common bases for this, what I would do is I would write log base 4 of 8 as log base 2 squared of 2 cubed. The bases are the same. Therefore, logs are exponents, and notice that the 3 is on top and the 2 is on the bottom. So that's kind of a nifty way of dealing with that, and that sort of gives like a modified logs are exponents law. Let's just keep it in part law 3. Log base a to the x of a to the y is going to be y over x, something that looks like that. Okay, so when we take a look at our next one, maybe I'll just do one more example of that. Here we go. let's say we wanted to evaluate something tricky. Log base square root of 5 of, I don't know, the 7th root of 25. Ooh, that looks terrible. Well, what I can see is my common base is 5. So the square root of 5 is 5 to the 1/2. 25 is 5 squared. So I've got the 7th root of 5 squared, so that's 5 to the power of 2 over 7. My bases match, so I'm going to get 2 over 7 divided by 1/2, which is 2 over 7 times 2 over 1, which is 4 over 7. And we can do all of this, funny enough, without our calculator, which is great. All right, I think I'm on property number 4. So property number 4 excuse me, has to do with log base A of 1. So again, what we would want to do is we would want to write 1 as a to the power of something. And so that's going to be a to the power of 0. So whenever you have log base A of 1, keep in mind that those properties matter. So a is greater than 0, a is not 1. But log base A of a to the 0. Out pops your exponent. And so what we get is that log base A of 1, doesn't matter what the base is equal to 0. So that base could be log base 3 of 1 or natural log of 1 or anything like that would be equal to 0. And our last one is this. This is kind of a weird one, and I want to show you how this property comes about. A to the power of log base A of x is equal to x. There's the property. I'm going to show you how to prove it. So let m equal a to the power of log base A of x. And what I essentially want to do is I want to show that m is equal to x. Now the reason why I want to show you the proof for this thing is because I want you to see what you can do with logs. So what I'm going to do for this first one is I'm going to log base A both sides. Just like you could square root both sides or add 5 to both sides, I'm going to log base A both sides. So we're going to log both sides here. So we're going to go log base A of m is equal to log base A of a to the power of log base A of x. Now this seems like a lot, but on the right-hand side, what you've really got is log base A of a to the something. And remember that that something pops out because logs are exponents. So we have log base A of m is equal to log base A of x on this side because the exponent right here pops out. Now by comparing the two sides, you can see that because it's equal, right, the two sides have to be equal and the log base A and the log base A are the same, therefore the m value and the x value has to be equal. This process can be considered as comparison, but is also sometimes called anti-log. So we are not dividing by log base A. There is no such thing as log base A by itself. It is like having a square root by itself. You always have to have a number inside of it. So what we are doing here to get rid of our log base A's is we are anti-logging. So what we have shown then, after all of that proof, is that a to the power of log base A of x is equal to x. And for example, if you want, if I had 2 to the power of log base 2 of 37, this would equal 37, and that's how we can evaluate using this property. Okay, so I've given you some examples about how everything kind of works. I thought what I would do is go back and just show a couple of questions to see how things go. So here are things that you could be asked to do. You might be asked to, 1, change to exponential form. So if I wanted to change to exponent form, what I would have to do is I might have something like y equals to log base 3 of x. Well, what we want to do to change to exponent form is, remember, you ask yourself, what's the base? The base is 3. Logs are exponents, so logs equal exponents, 3 to the y, and then our leftover number. We also want to be able to change to log form. Okay, so if I wanted to change to log form, 2 to the 6 is equal to 64. I'm going to change that to log form. So I ask myself, okay, it's a log. What's the base? Well, the base is going to be 2. Logs equal exponents. The exponent is here, and then the leftover number is going to be 64. By doing this, what we can do is we can actually find the inverse equation for functions. So for example, if I had f of x is equal to 2 log base 3 of x minus 1 plus 5 or something like this, let's find the inverse. So I'm going to switch everything. So x turns to y and y turns to x. So 2 log base 3 of y minus 1, and then plus 5. I'm going to isolate the log. So in all of these types of questions, you want to isolate the log or the exponent. So I'm going to subtract 5 from both sides. 2 log base 3 of y minus 1. I'm going to divide by 2, just like we did before in those questions. So we've got log base 3 of y minus 1. Now I'm stuck, but I know that my inverse of a log function is exponent function. So that means that I'm going to have to put it into exponent form at this point. So I ask myself, what's the base? Well, the base is 3. There's my base. What's the exponent? Logs equal exponents. So the exponent is going to be x minus 5 over 2, as ugly as that might be. And the leftover number is going to be y minus 1. And then all we have to do is we have to solve for y by adding 1 to both sides. So we get y is equal to 3 to the power of x minus 5 over 2 plus 1. Let's see, that's 3. The next thing that we were able to do is we were able to evaluate. So you want to make sure that you can evaluate something that looks like this, log base 3 of 27. That's going to be log base 3 of 3 cubed. Out pops the exponent. You want to be able to evaluate log base 27 of 3. So that's log base 3 cubed of 3 to the 1. Logs are exponents. You're going to get 1/3. And you want to be able to evaluate something like 3 to the power of log base 3 of 8. Bases match, out pops the 8. And you're going to do a little bit of practice questions, and you're also going to be doing homework day 4.